let's now try and create a formula for geometric series. Okay. So the first term will be a, second term AR, AR squared, and so on to AR n minus 1. This time I am going to write it down again like I did with the arithmetic one, but I'm not going to write it backwards. I'm going to multiply everything by r. So r lots of sum to the n. What that then does is it turns a into ar, it turns ar into ar squared, ar cubed, ar squared and ar cubed, and so on. And so again, I can do some sort of subtraction now, and I know I'll just be left with the first term of the top one minus the last term of the bottom one. So r minus 1, or actually I've done it the other way around. I've subtracted the top from the bottom. So r minus 1 lots of Sn would be the last term of the bottom one minus the first term of the top one. Everything else cancels. AR minus AR, AR squared minus AR squared, and so on. So divide by r minus 1, and I've also factorised the a, and there's a formula. Sum to n terms of a geometric series. Now, we tend to say, use this one if the ratio is bigger than 1. If the ratio is smaller than 1, then we go 1 minus r to the n on 1 minus r. So that's if it's smaller than 1. Reality is it doesn't matter. Because if you look at it, all I've done to get the bottom one is multiply top and bottom by negative 1. They are the same formula. I guess the reason why traditionally we do it that way, if r is a number bigger than 1, if I use the top one, I'm going to get a positive number. Whereas if I use the bottom one, I'm going to get a negative number on the bottom of the fraction. And if r is smaller than 1, then the top one gives me a negative number and the bottom one gives me a positive number. That's just really the only reason we tend to do that. You'll also notice I've got absolute value there. So if we have a negative number as our ratio, again, if it's smaller than 1, so negative a half, negative a third, whatever, we tend to use the bottom one. But if it's greater than 1, or the magnitude is greater than 1, so negative 5, then the top one we tend to use. Mind you, using that logic of creating a positive number on the bottom, you would think that if the ratio is actually, the magnitude is bigger than 1, but it's negative, then really the bottom one's probably a better one to use. Say that ratio was negative 5, then the bottom of the fraction would go 1 minus minus 5, and I'd end up with a positive number. But as I say, it does not matter. They are in fact the same formula. One's just been multiplied top and bottom by negative 1. Okay. But we also have this special one. This is a wonderful thing about maths. It is actually possible to find the value of an infinite number of terms. And you say, well, hang on, how is that possible? Because you're continually adding something, yet you can get an answer. It doesn't seem to make sense, because if you're continually adding something, then you're getting bigger and bigger and bigger and bigger. That's what we call the limiting sum. It only works if that ratio is smaller than 1. Because if it's bigger than 1, then yeah, it is just going to get bigger and bigger and bigger, and you're adding bigger and bigger numbers. But if that ratio is less than 1, each term is getting smaller and smaller and smaller and smaller. And that's why we can add them, because eventually we're going to get numbers that are so close to 0 that they're insignificant. And that's how we can come up with an actual answer for it all. Right? Because remember, we know this. If you think of your curve, if you were to draw r to the power of n, so your exponential curve, as n approaches infinity, and this is if r, the value of r is a fraction, so r to the power of n, you're saying like a half to the power of n. So it's your exponential curve that when you draw it, as n approaches infinity, it'll get closer and closer to the axis, or closer and closer to 0. So therefore, we're basically using limits, hence why it's sometimes called, instead of the sum to infinity, sometimes it's called the limiting sum, because that's what we're really doing. We're saying, well, what is the limit as n approaches infinity of a 1 minus r to the power of n on 1 minus r? Well, the r to the power of n is approaching 0. So therefore, that limit would be a on 1 minus r. And now, there's nowhere to substitute n into, So it doesn't matter that I've got an infinite number of terms. I can work out the answer. The sum to infinity is a on 1 minus r, but as I say, make sure that ratio is in between -1 and 1. Oh, there is one ratio we don't have to worry about, though, that's in between -1 and 1. What would it be? Yeah, remember that one we looked at yesterday? They went -1, 0, 0, 0, 0. Obviously, that particular one, the sum to infinity, if we were to ask that sort of question, would just be whatever the first term is, because every other term is 0. Mind you, there still is that question. Is it a GP? I don't know. Let's find the sum of the first 10 terms of this particular GP. So 2, 6, 18, and so on, and so on. So let's extract the information we know. First term's 2. I can see by inspection that the ratio there is 3. We've got 10 terms. So there's our formula, sum to n that I'm going to use. Subbing in 3 to the power of 10 minus 1 over 3 minus 1. Now, I must admit I set this question up quite nicely. So that, oh, look at the bottom, 3 minus 1's 2. That cancels with the 2. How lucky am I? So I get 3 to the power of 10 minus 1, which is 59,048. Of course, they don't all work out that nice, of course. Here's one in sum notation. The general term, so we can see that it is a GP because it's in that form AR to the n minus 1. But notice we're going from 3 to 8 for this one. So we've got to be careful with this one. So let's extract out the information. The first term is not actually when n equals 1 for this one. It's when n equals 3. So it'll be 6 times a half squared, which is 3 on 2. The ratio, well, that's a half because it's still the formula AR to the n minus 1. Now, if you don't immediately see that's the ratio, well, then all you do is work out the next term and then do a division and go, oh, right, that's the ratio. And be careful with the number of terms. As I said, well, 8 minus 3 is 5, but it's inclusive. So there's actually 6 terms here, not 5. Or I'll use the 1 minus r formula for this one. Let's sub in. Now, depending on how good your calculator is, how you would approach this. Some calculators can handle you just putting this all in like that with fractions, and it'll come up with a nice, neat answers. Some doesn't. Some just go, oh no, can't cope. I'm going back to decimals. So if it is like that, and I must admit, I tend to think that way as well, that, oh no, it's going to go to decimals because I'm old and my calculators are old. And so I got used to doing the other way. So I tidy mine up like this. I said, well, okay, I've got 3 on 2. And then I know half to the power of 6 would be 1 on 2 to the power of 6, which is 64. So 1 minus that would be 63 on 64. Then the bottom of the fraction's a half, so invert and multiply 2 on 1. And then I can look at it and go, well, look, 2 cancels with the 2, so 64 is on the bottom, 363s. That's how we used to do fractions, by the way, up here in the amazing. And it works too. 189 on 64 as my answer. So as I say, just be careful with your data entry and fractions if you're going with your calculator there. And certainly with some powers, as I say, can just go to a decimal. So the question is, does this particular pattern have a limiting sum? It's the sort of question that sometimes I like to ask because they want to know, do you know the condition for a limiting sum? Well, the condition was the ratio had to be in between -1 and 1. And that's basically what we're trying to find here. Well, what is our ratio? 4 on 56. I should have really checked this one to make sure that's also 4 on 56. What is it? 2/7 divided by 4. Is that 4 on 56? Yeah. Is it? Oh, yeah, of course. Yeah, right. Good. It does work. The ratio is the same. It is less than 1. So, yes, this particular pattern would have a limiting sum. Okay. Don't just say, yes, it has a limiting sum. Make sure you mention the condition so they know that you're not just guessing, because obviously it's a 50-50 chance to get it right. How's the cockroach doing? Has he made much progress there? I just noticed you're checking on him. All right. Classic paradox question. Frog in a well. You ever heard this sort of question? where you got a frog sitting in a well. You can substitute it for other animals in other conditions. It wants to get out of the well. But each time it jumps up, it can only jump half as much as it did the previous time. So the first time it jumps halfway up the well, then it jumps another quarter, then an eighth, and so on. And the question is, does the frog ever get out of the well? So let's see. If we were to add up an infinite number, a is a half, in this case the ratio is also a half, the sum to infinity, a on 1 minus r, and we have a half on 1 minus half, which is 1. So no, the frog does not get out of the well. Because it would have to be greater than 1 to get out of the well. I throw this question in here. One of the first questions we saw at the start of the year, questions like this, right? 0.36 repeater as a fraction. And the first way we saw to do it was using simultaneous equations, you might remember. And we said let x equal 0.36363636. And then we would have said, oh, well, then we'll let 100x equal 36.36363636. Do a subtraction. Then I showed you the quick way of doing it and said, well, hang on, there's a pattern here. I can just look at this and say, oh, that's 36 on 99. Okay. Now, there is a third way of doing it, and that's using sum to infinity. So let's rewrite 0.36, but I'm going to rewrite it like this. 0.36 plus 0.0036 plus 0.000036 plus 0.00000036 plus 0.0000000036 plus 0.0000000036, and so on and so on and so on. And we've got an infinite sum there. The first term is 0.36. The common ratio is 0.01. So the sum to infinity, a on 1 minus r, I get 0.36 on 1 minus 0.01, which is 36 on 99. Well, it's actually 0.36 on 0.99, but of course we don't have decimals in fractions. So multiply top and bottom by 100, and you get your 36 on 99, which is 4 on 11. So it's yet another way of solving that particular problem. So make sure you read the question. If it simply says, like I've done, write 0.36 repeater as a fraction, you just write the answer down. But I was 36 on 99. However, if they said, write 0.36 repeater as a fraction by expressing it as a limiting sum or by expressing it as an infinite series or something like that, then they're wanting you to use this sort of idea. Oh, okay, we're going to turn this into a geometric series and we'll find the limiting sum of that. So yeah, make sure you read the question to see if they aren't actually asking you to do it a specific way.